This is tutorial 7 and problem 13.42. In this problem we have a Venturi meter and it is at an incline of 30 degrees, and connected to it we have a manometer. The one leg of the manometer is connected before the Venturi in the pipeline, and the other one is connected at the throat of the Venturi, and the pipes are facing upwards and they have air on the inside of them. So the deflection of the water inside the manometer, the difference in height is 1.2 meters. And we're also given the diameters of the pipeline, which is 30 centimeters, and of the Venturi throat, 10 centimeters. So we're asked to determine the flow rate based on that deflection. The water is at 15 degrees C. We can look up the kinematic viscosity to be 1.14 times 10 to the minus 6 from table A5. Okay, how do we go about this? We've got to first of all find the flow coefficient of this system, the Venturi, and we have a delta H, which we know is 1.2 meters. We also know D over D, which is the throat versus the pipe ratio, is 100 over 300, or 0.333. The other thing we need to look up the flow coefficient on our table, which is on page 490, we need the Reynolds number divided by the flow coefficient, the value of that. And we can determine that by taking the diameter times the square root of 2g delta H over nu. Right, so that is in terms of the height of the change in height and the diameters. So substituting into that formula, we've got 0.1, which is 100 millimeters, that's the throat diameter, times the square root of 2 times 9.81 times 1.2 meters. That is the deflection, the difference in height in the manometer. So that's delta H. And we're dividing that all by the nu value, 1.14 times 10 to the minus 6. So that will give us an answer for that expression of 0.4256 times 10 to the 6. Looking on that graph, we can use these values, the d over d of 0.33 and the RED over k values that we just calculated, and we can look up our k flow coefficient, 0.97. So I'll just write here, figure 13.15, page 490. The next thing we have to do is use our Venturi equation. To determine the discharge. So the discharge is equal to Ka times the square root of 2gh. And we have all of those values. So we know what K is, that's 0.97. The area is pi over 4d squared. 0.1 is the diameter, and 2 times 9,81 times 1,2. From there, we can get a discharge through the Venturi of 0.04 cubic meters per second. And that is what we were asked to calculate in this instance.